we should do a new color today. What do you guys? What are you feeling? Teal? I heard teal first. That one I like. All right, what homework question do you have for me? Megan. Oh, I'm good. I'm good. Gavin.
I'm 7.
You're 7, you said? I look older than that, but okay. You're planning to make an open rectangular box from an 8x15 piece of cardboard. Okay. 8, 15. My hint to you is to cut some corners. The corners are X by X. So Gavin, stay organized. Step 1, diagram. Did you draw the diagram? Excellent. Check. Step 2, what's your objective equation? Gavin, help me out. Volume is L times W times H. And specifically, our objective is to maximize Did I do a V or did it just glitch? Did I do a V? No help, really? Nobody's watching. All right, maximize volume. Maximize volume. That tells me my constraints for step 3 for you guys, weren't they? Constraints. My constraints are going to be L, W, and H. Hopefully as functions of X. Gavin, did you get that far? What did you get for L?
15 minus 2x.
I like it. If you cut out X, then the length is 15. Take away 2 X's. And you guys did this last year in pre-calc, I believe, didn't you? Width? 8 minus 2X. And height? X. Yeah, you're folding up the flaps, right? You see it? Do you guys understand? Let me ask you this. Do you understand how you make this box? Ready? Watch up here. Look at the scissors. Watch. Ready? And then you cut out the squares, and then you fold up this flap along this dotted line. It gets folded up. You fold up this flap, fold up that flap, fold up that flap, and you got an open box that's 15 take away 2x, 8 take away 2x, and watch this. Watch. X. X. Y'all see it?
Very nice visual.
Thank you. I do this in my free time. And I cut out triangles for another class, but we're going to try. We're not going to have time before break, but after break, we're going to try to do this box activity. Okay? We're going to do this. Gavin, we're going to make these boxes. Okay? Just don't tell your parents you're going to be boxing, all right? In calculus class. It will not be happening. Boxing. And then we're going to find out what the maximum volume is we can put in that box. I don't know. Maybe put some old Pokemon cards. I don't know. What else could we put in the boxes? Huh? Pickles?
Some fruits, oranges.
Oranges? I mean, it's not going to be very watertight. Because, I mean, that seed. Ooh, you know you could get really fancy with, Gavin? Cut along this right here. Cut along right here. And that would allow you to fold it up, and this flap can wrap around the corner to give it extra stability and just tape it. You know what I'm talking about? You following me?
Whoa, it's low paid. It's low paid.
We could ship stuff in these boxes. West Falls box making company, where everything is maximized. Like we have tagline, t-shirts. Maximize your shipping potential. I like it. All right, back to the story. This is our objective. These are our constraints. Our volume is now x times 15 minus 2x times 8 minus 2x. We plug our constraints into our objective. I need to see this step. Now, we got kind of rushed yesterday. So step 4, plug the constraints into the objective. Step 5 it's very important. All right, don't rush step 5. Step 5 is your first derivative test. Now, you have technology to use for the first derivative test. Here's what I need to see, and you may use technology for this. If this is v, I need to see v prime of x. We're going to fill in the blanks. I need to see v prime of x. I need to see the critical points. And then I need a justification. Justify. This is what I need to see since most of this is done with technology. These are the checkpoints I need to see. Everybody understand that? So you may use your calculator for that. Ready? Calculator. Now, I had some questions on how do I do this in a calculator. I'm going to give you 2 options. Let's start off with a calculator window. I'm going to show you guys some neat tricks today. Ready? We haven't used these a lot, so this is the portion where I'm going to kind of train you how to use these with some nice tricks, as well as solving this type of problem. Actually, no. Let's go to a calculator window first. Calculator window first. We have done a whole chapter and more on derivatives. You learned power rules, chain rules, product rules, quotient rules, all sorts of rules. Now that we have mastered those rules, we're allowed to use technology to get us that part of the way. So here we go. If I want to take a derivative now in my calculator, see the templates button to the right of the 9? This is our first derivative button. We could do a second derivative. We could do an nth derivative. Ooh. Here we go. First derivative with respect to x of the function x times parentheses 15 minus 2x times parentheses 8 minus 2x. Hit enter. That is your derivative of your volume. That's the derivative of volume. That is your v prime of x. Are you with me? 12x squared minus 92x plus 120. 12x squared minus 92x. Was it minus 120 or plus? Plus 120. Could you have FOILed this out and expanded the x or multiplied the x in and then done it by hand? Yeah, please don't. Okay, you're just asking for trouble. Critical points is my next checkpoint. Critical points. You get critical points when you set the derivative equal to 0. I'm showing you how to do this in a calculator window. This can also be done in a graphing window. Here we go. Menu, algebra, solve. Or you could just type in the word on your keypad. You could type in the word solve, and it will recognize the command. Is that a question? No. Solve. What do we want to solve? We want to set the derivative equal to 0. Okay? If you hit up, it'll highlight. Yours should only click up once. Everybody see that? Control C right here. Control C will copy. Go down there. Control V will paste. Okay? That's our derivative. The equals button is right here. 2 buttons to the left of the 7. Equals 0. The comma is way down here to the left. Comma x. We're telling the calculator to solve that equation, comma x, with respect to x. Solve it for the x variable. it can solve multivariable equations, so you have to tell it which variable to solve for. If I hit enter, there are my critical points. That's where the derivative equals 0. 5/3 or 6. So I go back to my process, and I tell the teacher, x equals 5/3, x equals 6.
I got an error message.
You never said equals 0 at the end. So instead of typing all that again, up, hit enter. You want to set it equal to 0. Okay, comments. Everybody good? Wayne. Jake. Is it blinking green in the top? Yeah, it's a trusted test. Blinking green in the top?
Yes.
Alright, that's a problem. I need to do something to it later. Here's the problem. Just because it's a critical point doesn't mean it's the extrema we want. Do you agree? Okay. So justify, and I guess I'll add one more checkpoint. You're gonna have to label. You're gonna have to label which one it is. Absolute max, absolute min, or local max, local min. And honestly, it's gonna be the answer to the question being asked. It's an application problem. So here we go. How are we going to figure out which one of those critical points yields a maximum volume? Probably be easiest to graph the function or derivative. And I need you guys to really listen. Okay, I'm giving you some really important tips that will help you later on. Is it better to graph the function or the derivative? If we're graphing the function v, what are we looking for? We're looking for the peak on the graph. If we graph volume, we're looking for the peak on the graph. If we graph the derivative, we're looking for where the derivative changes from positive to negative. What if the volume is way up at like 5,000 cubic units? Scroll. See where I'm going with that? What if you graph the derivative? What are you looking for? An x-intercept. You know where to look. You're looking at 5/3 or 6. And what are you looking for there? Where the derivative changes from positive to negative. Do you see how that's beneficial? What did I do yesterday? Yesterday I graphed the original, and it was like 1.122. It's good to be able to do both. Do you see what I'm saying? I'm going to say it one more time. It's good to be able to do both. On one, I'm just looking for a peak. That's nice. But what if the peak's way up? Oh, okay. I don't feel like scrolling for days. All right. I'm going to graph the derivative and look for the x-intercept where it changes from positive to negative. Are you ready? I'm going to graph the derivative. Let me show you a tip. That's the derivative. I think I still have it copied, but I want to be safe. Control C. Home. Graph. Control V. Enter. We're looking at the graph of the derivative at my critical points were 5/3 and 6. 5/3 is 1 2/3. Do you agree? 1 2/3. The derivative changes from positive to negative at that critical point. That critical point just earned the title of maximum. This critical point, 1 2 3 4 5 6, where we thought it was going to be, this critical point just earned the title of minimum. We don't want that. We don't want the minimized volume. This is 4th period box company. We don't minimize volume. That's for 7th period. Boom, roasted. All right. We want to maximize the volume of this box. So even though you had to give me both critical points, this is the one that will yield the maximum volume. So ready? Here's another option. If you didn't go through the whole calculator tab option. Ready? Menu, analyze graph. Aren't we looking for a 0 on the derivative? Didn't we set the derivative equal to 0? Click on the left, click on the right. 1.6 repeating, which is 5/3. 1.6 repeating is 5/3. We just confirmed that x equals 5/3 will yield the maximum volume. Okay? There is a maximum volume. Justify. I don't have time for this. I'm sorry. We just took half the period on part of this problem. Okay? We've justified these before. There's a maximum volume when x is 5/3 because the derivative changes from positive to negative. Boom, done. Let's answer the question. What did it say? Find the dimensions and the maximum volume, I'm guessing. What are the dimensions of the box of largest volume, and what is the volume? Well, my dimensions, one of them was x. 5/3. The width, 8 minus double 5/3. You can do that. Length, 15 minus double 5/3. Volume. Well, that one I want to do. Okay. You could once you found the L, W, and H, you could multiply them out. Option 2, go back to this. Wasn't this our volume function minus the derivative part of it? It could just copy that, couldn't it? Here's a little hint, another hint. If you click to the right or left of where you want to copy something, if you hold down your shift button and click left or right, it'll highlight what you want. Shift, hold down shift and click, and then I can copy that, paste it. Okay, now I want to graph it. I'm going to hit tab to open up a new line. I'm going to paste the volume in. Now, I know this is a lot, guys. I know this is a lot. Just hang with me. I'm trying to show you as much as I can in as little amount of time. I want the volume at 5/3. Okay. Which graph is the volume graph? I would say magenta, but whatever. Okay. Menu, trace, graph trace. If I type in 5 divided by 3 and hit enter, okay, it's telling me 0 because I'm on which graph? The black, the derivative. If I hit the up arrow, it'll jump up to the purple, magenta, pink graph. 90.741. 90.741 is the volume at that x value. 90.741. This is a calculus question. Therefore, this part of the question is very important. I want the derivative. I want the critical points. I want the justification. I want the label. There is a maximum volume when x is 5/3, and the maximum volume is 90.741 cubic units because the derivative changed from positive to negative. Is everybody clear with what's expected? I'm trying to lay it out for you right now. If you want to write it down, put it in your notes. Wendy.
Can you show me how to go back to find the 90.7?
Absolutely. 2 ways to do it. 1, menu, trace, graph trace, and if you type in any x value and hit enter, it'll give you the y value. So I want the y value at 5/3. So I typed in 5 divided by 3. I hit enter. And if I wasn't on the right graph, I either hit up or down to get the y value on the other graph. Make sense? Option 2, go back to my calculator window, and everywhere I see an x, type in a 5/3. Okay? Is this overwhelming? Are you guys okay? Okay. There's other ways to do it. I don't We don't need to get into that today. I call this glitchy. No. I call this a visual first derivative test. Why? Because you can see the critical point because it's where the derivative crosses the x-axis, and you can see how the derivative changes sign. Do you agree? It's a visual first derivative test. The AP test, they love to do that. I'm going to say it again. You will see a handful of questions. There's not a ton of questions on the AP test, okay, in the grand scheme of things. You will see a handful of those first derivative tests, okay? Explain what is happening at x equals 5/3 based on the derivative graph. There is a local max at x equals 5/3 because the derivative changes from positive to negative. Done. Easy. No calculations at all. Look at a graph. All right. Gavin, you good? Awesome. Can time. The can. What's our objective? Nope, picture. Oh, I have to draw a can. I can. All right. You've been asked to design a pop can that can hold 356 cubic centimeters. All right, I made it 12 fluid ounces, so it's realistic. Okay? I hope from now on, as you read these problems, that the constraint jumps off the page at you. As soon as you, I don't want to say this happens all the time, but when you see a number in a problem like this, do you agree that's going to hold you back? It's a constraint. You're only allowed to use 1,000 feet of fencing. Constraint. You're only allowed to use 356 cubic centimeters of liquid. Constraint. That should tell you what the constraint is. And that unit of measure should tell you what equation involves the constraint. What dimensions will use the least material? Minimize surface area. That's my objective. So when we draw a can, it has a radius, it has a height. It's a radius, has a height. 2, objective, minimize surface area. So I'm thinking to myself, okay, well, what's the surface area of a can? Next question. Is this can fully enclosed? Meaning, does it have a top and a bottom? Sometimes they'll say it's an open top cylindrical can. If they ever use the word right cylindrical, that means the base is perpendicular to the height. It could be oblique cylindrical. Remember Cavalier's principle? The volume of a right cylinder is equal to the volume of an oblique cylinder with the same height. You ever see that? Geometry? Okay, you know a spindle of like CDs or DVDs way back in the day? Used to make my girlfriend mixtape, mix CDs on there. Some Boys to Men's been saying. Never mind. When you put the CDs on the cylinder, it's a right cylindrical spindle. If you take them off and you're like, oh, this is fun. You guys probably never had the pleasure of doing that, did you? Did you ever use CDs? Did you? Okay. You know how you take a stack of CDs and you tilt them? It has the same volume, doesn't it? Even though it's tilted? Because as you tilt it, it still has the same height. Same volume. Good story. All right. How do you find the surface area of a fully enclosed can? Do you know this? This would be an equation I would give you, but do you know it? Well, it's got a top and a bottom, so it's got
The area of a circle times the height.
So, I don't know what that is. A G? Let me give me the tiny eraser. All right, surface area. we've got a circle on top and a circle on the bottom. So we have two pi r squareds, right? A top and a bottom. 2 pi r squareds. Plus what we called the lateral surface area. Did you ever find the lateral surface area of a cylinder? No? Tyler. 2 pi RH. You're my boy. You're my boy. 2 pi RH. Where'd you get that from?
It's the circumference of the circle multiplied by the height.
See, he's a big ideas guy. Okay, I like it. 2 pi RH. Now, here's where he got that from. Pretend this is a soup can that has a label. We won't say Campbell's for fear of copyright infringement. Oops, I said Campbell's. All right, cut the label. I'm recording this too. I apologize. Please don't sue me. I know they're listening. We cut the label. We unfold the label. It is now a rectangle. And Tyler says if you take that rectangle, its length is the circumference of the cylinder, 2 pi r. And this is the height of the cylinder, length times width, 2 pi r h. Do you agree with Tyler? I do. And if you take the lateral surface area and the top and the bottom, you have your objective equation. Surface area is 2 pi r squared plus 2 pi r h. Let the objective equation tell you the constraints as well, okay? Let me back up on that. I'm going to take part of that statement back. It's not going to necessarily tell you the constraints. It may tell you some of the variables used to involve the constraint. The real constraint was how much volume it can hold. Do you agree? That was a constraint. Hold us back. So step 3, identify your constraint. Well, our constraint is that the volume, did I say 356? 356 cubic centimeters. Well, wait a minute. So I have to involve the volume of this thing too? What's the volume of this thing? As an equation. Area, capital B times H. Area of the base times the height. What's the area of the base? Pi r squared times the height. Pi r squared h. And the volume we're working with is 356. Is that good or are you guys confused? You good? You're like, as long as you're doing it, I'm good. All right. What's next? Plug the constraint equation into the objective equation. Plug the, oh, wait a minute. Plug the constraint into the objective. Well, it's not solved for anything, is it? How are we going to plug it in? Decision time. Would you rather solve that constraint equation for H or for R? H for sure. If you solve for R, you're going to have to divide by pi h and square root. Plus or minus the square. No. If I want to solve for H, I just have to divide by pi r squared. So H equals 356 divided by pi r squared. And we're plugging that in where? Into the objective. my surface area is, it's 2 pi r squared plus 2 pi r h, 2 pi r squared plus 2 pi r h. That just reduced this whole problem down to two variables, but s as a function of its radius, okay? S as a function of its radius. What do we want to do with this thing? This is a surface area. We want to minimize it. Minimize it. Okay, now we're doing the first derivative test on it, okay? Now, wait a minute. I don't like to type in any more than I have to. So if algebra makes you nervous, that's one thing. But if you can clean this up just a little bit, you may find that you're typing in a lot less in the calculator. Do you agree this is over 1, right? And r cancels out with one of those r's. The pi's cancel. Double 356 is what? 712. I don't know why. I did not mean to write an equal sign there. Seven 712 over r. That is our objective equation with the constraints plugged in. All right, decision time. Are we going to graph the surface area and look for a valley, or graph the derivative and look for where the derivative changes from negative to positive? Huh? Derivative? Okay. Let's do 2 pi squared plus 7 r. Let's do this first. I told you guys I wanted the critical points. So we're going to do the derivative. We'll get the derivative, and then we'll graph the derivative and look for those critical points. All right. Got 2 pi x squared plus fraction 712 over x. Is that right? All right, we're taking the derivative of that guy. Got it. And that makes sense. Remember how the derivative of 1 over x is negative 1 over x squared? The derivative of 712 over x is negative 712 over x squared. We could have done that by hand. That's fine. We want to set this thing equal to 0. So I'm going to copy it up, Control C, go down. We're going to menu, algebra, solve. We're going to paste in the derivative equal to 0, comma x to get our critical points. Ugh. It has one critical point, and it is ugly. Wow. Can I give you a little hint as to get the dust? I would not, like, remember how the last problem I put 5/3? Fine, 5/3. Keep it 5/3. Don't round. This one, round. You don't want to write this out. Ready? Control Enter will give you the decimal approximation of that fraction. Control Enter gives you that decimal approximation. And some of your calculators might not have even given you that fraction. Some of the settings on your calculators already gave you that decimal. 3.841. But just because you got one critical point doesn't mean it's the minimum. Okay? So let's pair this with a graph. Do you remember how I still have the derivative copied? Let's go to a calculator graphing window. Control Paste. Enter. Oh, look at 123.841. The derivative, that green graph is the derivative, changes from negative to positive. I feel confident that that critical point yields the minimum surface area when x is 3.841. Five, critical point. R equals 3.841. Your justify would be the derivative changes from negative to positive. Your label would be a minimum. Bless you. Bless you. And let's read the directions. What dimensions will ye use the least material? Well, the radius is 3.841. The height, and then we want the surface area. How do we get the height? Look for the easiest function to plug R into to get H. Do you guys see it right here? You're going to find this. When you go back up to your constraint step, you're going to find that if you're trying to find another one of the constraints, I bet it's probably already solved for because you had to do substitution, right? Make sense? So if I plug in 3.841 into this equation, I'm going to get what the H. Anybody type it in? You're lazy. Type it in. Your button is broken. Goodbye. It's going to change your life, friends. What is it? What's the height? Huh? 7.79. It was 0, 0. Just get in that habit. I'll put a 0 there. I know it though. Not need it. Anybody else get that?
I got 7.6.
7.68?
Yeah, that's right.
Wendy.
It's okay. We'll forgive her. She offered an answer. What'd you guys get? 681?
Yeah.
Come on. What do you notice? What was the radius again? 3.841. It's double. The height is double the radius. Oh, wait. The height and the diameter are the same. To maximize, to minimize the surface area of a can, you want the height of the can and the diameter of the can to be equal. So wait a minute. Why don't the pop can manufacturers do this? It's hard to hold. And who's your market?
People.
Yeah. You can't have little kids who want the pop. You can't have little kids with it. They can't hold it. What are you gonna do? And they're like, oh, I want pop, but they can't hold it. That's your market. Little kids that have zero self-control. That's your market for pop. No, I'm just kidding. Do you agree it'd be hard to hold? So even though it's the optimal design, it's not the most utilitarian in nature. Changing lives one pop can at a time. So maybe it's the canned chicken breast and tuna. Maybe they're after that, right? Aren't they like shorter and squattier? All right. Anybody get the surface area that was minimized?
I got 217.069.
278.069, and that would be square centimeters. I believe we use cubic centimeters for volume, didn't we? So that would be how much aluminum is used on that top can. That was fun, wasn't it? That was fun. How many of you actually enjoy that application? Interesting. The boxes are really going to change our lives. We start shipping out stuff, optimized. People are like, actually, interesting fact, Amazon has thrown that out the window. Okay, and this is, in all honesty, I have a friend who actually is a manufactures boxes. Okay, Amazon's method of optimizing, you know, when they send pack. Have you ever noticed if you get an Amazon box, it's like this big and there's like one little thing in it? Because they can produce so many of that type of box, and they have such bulk shipping rates, they don't care about the time it would take to find the best size box and to make that box. That's a waste of their time. They could just make this size of box, and they already have really low shipping rates because UPS want an account with Amazon. Postal Service wants an account with Amazon. They're like, oh, we're only going to charge you this much. We don't care what size the box is. They don't care anymore. They just want to minimize the cost to ship, not necessarily the volume of the box. Take that with you. All right. I am going to have you, I did not print these out, but on the 4-4 worksheet, if you click on it, let's see how many we have circled here. 1, 2, 3, 4. Just 4. 1, 2, 3, 4. All right, here's what I will tell you. For number 2, build a rectangular pen with 3 parallel partitions. I'm going to help you out with this one. Rectangular pen. Ready? What's a partition? Like a little divider, right? 1, 2, 3 parallel partitions. So guess what? When you're using fencing, 500 feet of fencing, you have to use fencing on those partitions. They only give you 500 feet of fencing. Your constraint is, what's holding you back? The fencing, which is what component of this picture? Perimeter-ish? Listen,
What's the press test?
we're going to have to dock it with another calculator.
Oh yeah.
I don't know.
Nobody's walking around sipping soup.
Right. You just hold it for a
Well,
little
you
bit.
get more soup. More soup cans. Yeah, more soup per can.
So would I be
It's the ratio.
yeah.
No,
would I
no,
be
you're
able to
wasting your
come
money
in
on
and
more
make my
tins. That's the entire point. You're wasting your money on.
Will you email me the day of it or like, thank you.
So if I like leave that here, take it off.
Yeah. I just need to find it.
Alright, I can come back 7:30.
If I might not have it done by then. I'll try.